Hi guys and welcome to the video. This video is going to be all about bladeless fans and the mechanisms that make up the flows that they create. So before talking specifically about bladeless fans, I'm going to introduce you to a phenomenon known as the Coanda effect. Here we have a shape known as an aerofoil. There are many variants of aerofoil, but the common concept behind all of them is that they are designed to be streamlined in an airflow whilst also being able to produce lift. The cross-section of an aeroplane wing, for example, is shaped like an aerofoil, and there are also many cases of aerofoils being found in nature, the cross-section of a dolphin fin being just one example. Now, when an aerofoil, such as this, is confronted with a uniform airflow, which just means it's the same all the way through it, so the same direction and the same speed, this is what happens. So the flow hits the front of the aerofoil here and it can't move through it, so it has to go around it like this. And the same thing goes for the flow underneath as well. Now, in being pushed around the aerofoil, this flow has actually been accelerated. So it's moving faster than it was. Now, according to this equation called Bernoulli's equation, if air is, or if any fluid is accelerated, then the pressure inside it will drop. So what you have is fast moving air here with a low pressure, fast moving air here with a low pressure. The air up here and down here is moving relatively slowly, so it has a higher pressure. This higher pressure up here pushes down on the lower pressure and causes the flow to stick to the side of the aerofoil effectively. And so it follows the shape around it like this. This effect is called the Coanda effect and has a few practical applications, including enhancing the lift on an aerofoil wing. And I'll show you that now actually. So if we were to change the angle of the aerofoil relative to the flow that's going over it, so if we make it something like, instead of this, we move it to there, then this is what happens now. So, as before, it can't go through it, so it goes up, and the Coanda effect still applies because it's been accelerated again and it sticks to the wing, or sticks to the aerofoil, I should say. And the same thing goes for it below. The air below is not, it doesn't undergo quite as drastic a change as the air above. It is not accelerated as much, and so here it is moving at a lower speed than the flow that's over the top here. Now, as I said before, the lower speed means that it has a higher pressure, and this pressure is exerting a force on the surface of the aerofoil in that direction. The air up here is also exerting a force on the surface of the aerofoil in that direction. But the higher pressure here from the slower moving air creates a, let's say a big force in that direction. The faster moving air here exerts a force downwards on the aerofoil, but it's not quite as strong because the pressure is lower. So we'll say it looks like that. Now, the resultant force, therefore, on the aerofoil, if we say that these two cancel, this bit here will cancel out that much of the flow of the force there, you see what I mean, results in a net upward force from what's left on the aerofoil. And this is part of what causes lift on airplane wings. So now I'd like us to consider what happens when we make a few modifications to this aerofoil. And we're going to take the flow away as well. So what we're going to do is hollow the aerofoil out and produce a flow from within it rather than from in front of it, as we just saw. And this is what it looks like. So you still have the general aerofoil shape. As you can see, it looks pretty similar. but it is hollow. And if the air comes from within it, such as like this, and then out this gap here, which is the only place it can go, it's moving fast enough here that the Coanda effect still applies, and it again sticks to the top of that surface there, being pulled outwards. So what's all this got to do with bladeless fans? Well, bladeless fans are, and if you don't know what they look like, I'd look up a picture of one right now. The hoop that you get in bladeless fans is actually made of this shape being revolved around a circle like that, and that creates the hoop. So if you were to cut a bladeless fan in half, imagine we have one that's like this. That's, my hands are the hoop and it's blowing air that way. You cut one in half, this is what you would see, with that being the top of the hoop and that being the bottom. And if you imagine the tower coming down here, like that. Obviously this isn't to scale. In reality this would be way further up there, but my board isn't big enough. But you get the idea. So unfortunately, the so-called bladeless fan is not actually bladeless. And in the tower down here, it has an impeller, which is basically, it's almost the same as a propeller. And it moves air. It pulls air in from the surroundings through holes in the tower and pushes air up there, where it goes into the inside of the hoop, and behaves as follows. Just as before, it comes out of this gap here, runs down there, and the same thing at the top as well, coming out here and down there. And the Coanda effect is causing it to stick to the surface. Now, because it's moving in a direction sort of that way and that way, it's leaving an area of low pressure here, which is the middle of the hoop. This low pressure area pulls air in from the area behind the hoop, which has relatively high pressure. So it pulls air in from here, and its momentum now carries it on through the hoop and out the other side into what you see as the flow being created by the bladeless fan. This process is called induction. So this flow is inducted flow. And that is one component of the total flow created by a bladeless, so-called bladeless fan. Another important component is caused by the flow boundary once it has left the fan. Now the flow boundary is what we know as turbulent, which means it doesn't travel in this nice straight line. It's constantly moving and swirling around in vortices like this. Now these turbulent vortices cause something called entrainment, which is where the air, as it's swirling around on the boundary of the flow, grabs air from outside of the flow and pulls it in. And once air is in the flow like this, then it's in it forever. And so this entrainment process is constantly adding more and more air into the flow itself. So the combined effect of induction and entrainment, we'll call this flow entrained, so the combined effects of these two flows mean that when the flow of the fan is fully developed some distance away, you can't see that there, we'll say, the volume of air in the flow at this point can be up to 15 times the amount of air that is here being drawn into the tower of the fan. So you can get an air multiplication rate of up to 15 times, which is pretty impressive. So that is how bladeless fans work. I hope you enjoyed the video and I hope you learnt something from it. Thank you very much for watching. Goodbye.